Hello, and welcome back to AP Physics. Physics is the study of matter and energy, but what is matter? Matter is something that takes up space and has mass, is what the definition of matter is. Matter has mass. And we also say that mass is the determination of how much matter is in an object. So what you get is this circular definition of what mass is, because people really don't know what mass is. They just know how mass behaves. And mass has two main properties. One, if you put two masses anywhere near each other, or two masses in the same universe, then they attract each other with a force proportional to their masses through gravity. And the other property of mass is the more mass an object has, the harder it is to get moving or stop moving. The harder it is to change what it's doing. Now, weight and mass are different things. Weight is a condition that mass undergoes. Well, it's a force. I don't know if you would say it's a condition. It's a force on a mass. Okay, but it's not it's not the same thing as mass. So force is weight is the force of gravity on an object. So if you go into space, okay, there's no gravity, you've got no weight, but did you lose any of your matter? Okay, if you go to the moon, did you lose any of your matter? You'd weigh 1/5 of what you weighed here. And the answer is no, you didn't lose any of your matter, you didn't lose any of your mass, but you would lose weight. Okay. Thinking of inertia, the harder it is to accelerate something. Let's say you've got a bucket, and you've got a small bucket, and you want to determine, you want to accelerate it, you want to kick it, playing kick the bucket. It's a fun game. We all played it. So if you kick an empty bucket, it goes flying. Okay, no big deal. It accelerates very easily because it doesn't have much mass. If you fill the same bucket with sand, it'll probably fall over and move a little bit when you kick it. If you fill that same bucket with lead, it's probably not going to move barely at all, and you're going to have an ouchie foot because the lead has more mass than the sand or the empty, well, filled with air technically, bucket. So the more mass an object has, the harder it is to accelerate, the harder it is to speed up and slow down. If you were to take a big old dump truck into outer space, and you were to, this is a very expensive project, and you were to, would it have any weight? No. Would it have any mass? Yes. Okay, so what you want to do is waggle it up and down. So let's say you grab the door handle, and you just want to shake this dump truck up and down. Well, what's going to happen is the dump truck isn't really going to move hardly at all, and you're going to be waggling up and down because you've got less inertia. You're easier to accelerate than the big old truck. Mass and weight are measured in different units. Mass is measured in grams, kilograms, or in the English system, slugs or pound masses. Weight is measured in pound forces. And newtons, and so your weights, you figure out your weight in pounds. So to recap, mass is how much matter is in an object. It's how much inertia the object has, which is how lazy an object is to change what it's doing to either speed up or slow down. And we're going to be using units of kilograms to measure it. Weight is the force of gravity on an object, and we're going to be using units of newtons to measure it. The equation for weight, so this is our first equation since the last unit, it's a super easy one. The weight of an object, F sub g, is equal to mg. Fg equals mg. Force of gravity equals mass times gravity. So it's a real simple equation. And so we'll be figuring out the weight of several objects to figure out some of the other forces when we apply this to free body diagrams. Okay, so if we look at what the units would be, if I take a kilogram and I multiply it by a meter per second squared, what I end up with is a kilogram meter per second squared, which is a newton. A Newton really stands for kilogram meter per second squared. It's obviously a lot easier to write and say Newton than it is kilogram meter per second squared. So, and of course they did it to honor Newton. So let's work a little bit of math with our new equation and apply to our free body diagrams. So draw a free body diagram for a 3 kilogram book sitting motionless on a desk and give the magnitude of all the forces. What if a hand pushed down with 15 newtons, and what if a rope pulled up with 15 newtons? Okay, so we'll work the first part first. So our force diagram for our motionless book, we've got the force of gravity down, and we've got the normal force up. We know that these forces are going to cancel if it's motionless. So if it's motionless, we know the forces in the x direction will cancel and the forces in the y direction will cancel. There's only 2 forces, so I know that the force of gravity and the normal force will cancel. Doing this a little bit more formally, what we're going to say is the sum of the forces equal to 0. We know that because it's motionless. So 0 equals the sum of our forces, which is going to be the normal force. Now we make it positive because it's up, and we're going to subtract off gravity, or we're going to add negative gravity because gravity is down. So 0 equals Fn minus Fg. And then solving, Fn equals Fg, which is basically what we figured out when we looked at our force diagram. So the force of gravity is equal to mass times gravity, which is 3 times 9.8 equals 29.4. And so I know that both of these are equal to 29.4. Okay. The next thing we do is we push down with 15 newtons of force. Okay, so we've got our force diagram. We know that things are going to cancel because it's still motionless. So we know that the forces have to cancel. And we can ignore x, the x direction, because we don't have any forces in the x direction. So we've got a normal force up, we've got a hand force pushing down, okay, and we've got a force of gravity force pulling down. So we'll write our force diagram. So the sum of the forces equal to 0. So that because of that, 0 equals then Fn, which is positive because it's up, minus the F hand minus Fg. Solving for well, not solving, plugging in for force of the hand, which is 15, and 29.4, which is the force of gravity we calculated before. We get that the normal force equals 44.4. So basically, these two have to cancel out with this, or this normal force has to cancel out the 2 downward forces. So that makes enough sense. And let's say we lift it up with that force of tension, that rope, this time. So we're going to say, again, it's stationary, so 0 equals. If an object isn't equal or is not changing what it's doing, it's 0 equals. Then Ft, which is positive this time because it's pulling up, plus Fn minus Fg. Okay, solving for Fn, it's equal to Fg minus Ft. So we have to subtract those. So and we get 14.4. Okay, so what we want to get into is what's called statics or static equilibrium. And statics is the study of things that don't accelerate. So it might sound like a very boring discipline, but there's lots of things that we don't like to accelerate, especially like buildings and bridges and there's lots of things we'd rather not accelerate. So what we're going to say is that our forces cancel. So the sum of my forces have to cancel out. My up forces have to equal my down forces, and my left forces have to equal my right forces. Okay, that's how it's going to work out. So we've got a girl, and she's at equilibrium. She's motionless. So we've got 120 newtons, which would be her weight, and we have got the tension in each cable would be 60 newtons. So that would be 120 newtons up. So I've got 120 up and 120 down. She's going to remain stationary. And by the way, we were just working some static equilibrium problems before we even got to that slide. So if it seems like, hey, we were already doing that, we already kind of were. So now, what would happen if I stretch out these chains? Would the force of tension go up, down, or stay the same? What do you think? Well, you might be tempted to say stay the same, and normally what I would do is I'd use a couple spring scales and I'd do this, and I would show you that the further I spread these chains apart, the more force that has to be applied to keep this thing from falling. So the further they're splayed, the greater the force. So if you can, picture yourself holding an empty swing with the chain. So picture the person is gone, and you're trying to pull this chain, or picture yourself just pulling a chain, and you're trying to make the chain perfectly flat. Okay, it's always going to have a little sag in the middle, no matter how much force you apply. The more force you apply, the straighter it gets. Okay, but you never get it perfectly flat. So let's work a static problem here. So we've got a 145 kilogram mass, and it's being supported by two cables. So we'll say both 50 degrees from the horizontal. Oh, I didn't work this problem. I wonder if I should. I've got one that's similar. So yeah, I think I'll skip that one. So maybe. Okay, so I was debating whether or not to do this problem because I didn't have it done. I skipped over it, but I do want to go ahead and go over it. So we start with our free body diagram. We've got the force of gravity pulling down on the mass, and it's 145 kilograms. So we would just figure out the force of gravity real quick because we're probably going to need it. Then we've got two force of tension vectors at equal angles. Now since we're going to be solving this, and we've got angles, we want to break these apart and do our components. So we've got FTY and FTX over here, and the same thing, FTY and FTX over here. Now, since these cables are at equal angles, the forces have to be the same, so we call them both FT. We also know that the FTYs have to be the same, and the FTXs have to be the same. So doing our sum of the forces equal to 0, because it is motionless. Okay, or if it was moving at a constant speed, it'd still be the same thing. So 0 equals, so FTY, and then minus RFG, minus 1421. And solving that, we get FT equals 1421. Now, once I know a side, I've got an angle and a side, I can figure out the hypotenuse of the triangle using sine. So the sine of 50 equals FTY over FT. So sine of 50 equals FTY, which is 710 over FT, and you get the force of tension equals 927 newtons. So that's that, which is definitely over. Adding these two will be 1800, which is over the 1400 that would be required if they were straight. The 1410, I'm sorry, the 710.5 if the chains were straight. Okay, so which one of these is more likely to bend, or more likely to break? The cable with the single cable, or the one with the double cable that's spread really, really far? This one is actually more likely to break because the further these are spread apart, then the greater the force is, and you'd have to apply an infinite force to get it to be perfectly flat. Okay. This one is kind of a tricky question, but something I'd pay attention to. Could be a test question. Which one of these cables would have more tension in it? We've got a diagonal one and a vertical one, a more vertical one. Okay, let's see if you can guess right. It actually is the one with that's more vertical. It's supporting more of the weight of the mass, if that makes any sense. But to look at it from a forces standpoint, we know that the x components of these forces have got to cancel. So the x component here has got to cancel with my x component here, because those are the only two involved. Okay, so that sets basically where my triangle, the ratio of my triangles. So for any given triangle, this one's going to have a much greater y component for a given x component. Since they have the same x component, this has a greater y component. The force of tension is going to be greater in that one. So that's what the vectors would look like. Okay, so here's a problem where we've got that same 14 or 145 kilogram mass, and now it's being suspended by two cables. We've got force of tension A and force of tension B. Okay, and then we're going to have force of gravity down, and we want to figure out what the tension in the two cables. Basically, the tension is just the force. What force is it applying? And that's all that's asking. So we draw a force diagram. So we've got our dot. The force of gravity is down. The force of tension B is to the right. Okay, it's perfectly horizontal because that cable is perfectly horizontal. And the force of tension A is upwards at a 50-degree angle. Okay. Now we want to break these components, these vectors, or the vector, into its components. So FTA we want to break up into FTAX and FTAY. And now we can start solving. So we're going to say that the sum of the forces in the y direction equals 0. So we know that there's one down force and there's one up force. So 0 equals FTAY minus FG. Again, something to note, once you break this vector apart into its components, you don't use the original vector anymore. Okay, that's double dipping. You only use the components. Okay, so therefore FG equals FTAX, which we know because we use hash marks anyway. So we're just going through the formality of doing 0 equals. And the force of gravity equals 145 times 9.8 equals 1421 again. I just used the same mass. Now to find the actual tension in the cable, we use our triangle, 50 degrees, 1421 and FTA. So the sine of 50 equals opposite over hypotenuse, so 1421 over FTA. So the tension in cable A is 1855. Lastly, we want to figure out the tension in cable B. Well, I know that B is going to cancel out with this X component here, so doing that a little bit more formally, 0 equals FTB positive to the right minus FTAX negative to the left. And so that tells us that they're basically equal. Okay, not basically equal, they are equal. And FTAX is just going to equal cosine of 50 times 1855. So just using that same triangle, cosine of 50 times 1855, so 1192. We're skipping that one. Okay, let's look at a crate being drug on first off, are there any questions? Okay, if you raise your hand. Okay, if there are questions, come to my office hours. Okay, don't forget about my office hours, 12:15 to 12:55. Speaking of which, I think I meant. Okay, so back to this problem. We've got a crate. It's being drugged at a constant speed by a rope. Okay, so here's my rope, which is 375 newtons of tension force at an angle of 25 degrees above the horizontal. And we want to figure out what all the forces are. Okay, so we want to draw a free body diagram, and then the other key information we want to take from this, well, we want to take all the information, but is that it's moving at a constant speed to the right, we'll say. That tells us that the forces are balanced. My forces in the X have to add up to 0, my forces in the Y add up to 0. Okay, so here's my force diagram. So for the crate, we're going to have the force of gravity down. Okay, we've got the 375 tension force upwards at an angle of 25 degrees. There's still going to be a normal force because it's in contact with the ground. Okay, and then there's going to be a force of friction acting to the left. Okay, it's moving at a constant speed. All right, let's go ahead and find what these component vectors are. So this one is going to be the sine times 375 equals 158. And for this side, we use the cosine, we get 340. Okay. All right, so now we're going to say the sum of the forces in the X equal to 0. So now we're only going to look in the X direction. We've got forces in the X direction and forces in the Y direction. We're only going to look at forces in the X direction. So we're going to say, all right, this positive 340 to the right, okay, minus my force of friction equals 0. Okay, and therefore the force of friction is 340, which we can go ahead and drop hash marks here, and we know that those are going to cancel. A little bit trickier. So we say the forces in the y have to cancel, because again it's moving at a constant speed. We've got 0 equals the normal force, which is positive because it's up, plus the 158, because it's up, minus Fg, okay, equals 0. So let's figure out what Fg is real quick. It's 559, and then plug that in and you get 50401. And this is where I'm going to stop for today after this problem. Okay. Sorry, a little bit of a long video. So here we've got to create with a mass of m, okay, sitting motionless on a theta degree slope. Okay, determine all the forces. So this is when we want to. Whenever you see something that's on a slope, you're pretty much going to do that rotating the free body diagram, rotating the page method, which I tried to explain, not in person. Maybe, hopefully, it's making some sense. So we know that it's stationary, so all my forces cancel. So we drew the force of gravity down, and then we turned the page so that the slope was flat. Okay, and then we draw our we break apart gravity into its two components, into a y component and into an x component. Okay, or this is the angle of the hill. So notice that the force of gravity should be your hypotenuse. Okay, should be your hypotenuse. If it's not your hypotenuse, you did something messed up. And your right angle, of course, is across from that. So this, the force of gravity is equal to mg. So just using sine, cosine, tangent, fgx is equal to the sine of theta times mg, the hypotenuse, sine of theta times fg. And fgy is equal to the cosine of theta times mg. Okay. We've got a normal force acting perpendicular to the slope, and we've got the force of friction, which is preventing it from sliding down the slope, so it's acting up the slope. So we've defined our coordinates as y is perpendicular to the slope, and x is going down the slope. Okay, so now let's look at our balanced forces. The sum of the forces have to add up to 0. So again, it's helpful if this is, I can't rotate this on the screen, but if you could turn it so that this is pointed straight up and that's pointed straight left, it would probably be easier to look at it. So so Fn, which is so 0 equals Fn, that's my positive, minus Fgy, okay, and then substituting in Fn equals mg cosine of theta. Now looking in the x's, okay, the x's have to cancel. So our fgx is positive, so 0 equals fgx minus ff, okay, where fgx is equal to cosine of theta mg, sine of theta mg, sorry. And that's how you work one of those problems. Okay. Well, that's where we're going to end for today. Sorry about the long notes. We went through a lot, so take a stab at the equilibrium problems. All right.